Okay, well, welcome everyone to the 16th annual Dean W. Lytle Electrical and Computer Engineering Endowed Lecture Series. I'm Eric Clavens. I'm a professor and the chair of UW ECE. In 1958, Dean W. Lytle joined our department, then called Electrical Engineering, as an assistant professor after earning his undergraduate degree in electrical engineering from UC Berkeley and his MS and PhD degrees from Stanford. Dean's research and teaching focused on communications networks and signal processing. During his 40-year career at UW, Dean was a beloved teacher, a mentor, and intellectual powerhouse of our department. He taught generations of students, authored 2 textbooks, and collaborated with engineers at Boeing, Honeywell, and Bell Telephone. Dean passed away in 2003, but his memory lives on in this lectureship. The Lytle Lecture Series was established in 2006, the centennial year of our department, through fundraising efforts led by Louis Scharf in collaboration with Marian Lytle and the Lytle family, Dean's graduate students, his colleagues at Honeywell's Marine Systems Center, and the UW ECE community. Over its 16-year history, the Lytle Lectureship has become our department's premier annual event, featuring researchers from around the world who, like Dean, work in communications, networks, and signal processing. I would personally like to thank the Lytle family and all those who have contributed to support this effort and make the lectureship a staple of our department. Now, I do have some sad news. Dean's wife, Marian Lytle, who attended all of the Lytle lectures, passed away this morning. The hearts of the entire UW ECE community reach out to the Lytle family, and we would like to dedicate today's event to her memory. I would also like to acknowledge everyone who organized this year's event and give a special thank you to the co-chairs of the Lytle Lectureship Committee, Professors Mariam Fazal and Rico Malvar. Mariam and Rico, thank you both for your leadership. Rico is a Microsoft emeritus researcher. He has had a long and distinguished career developing and innovating technologies related to data compression and signal processing. He is also a UW ECE affiliate professor and a longtime supporter of our department. Mariam holds the Morthy Family Professorship, as well as adjunct appointments in mathematics, statistics, and the Allen School. Her current research interests are optimization in machine learning and AI, learning and control, and online interactive and reinforcement learning. Mariam also leads the NSF's Institute on the Foundations of Data Science, which brings together mathematicians, statisticians, computer scientists, and engineers from across the UW and partner universities to develop the theoretical foundations of data science. She is also our faculty host for this event, so please help me welcome Professor Mariam Fazal, who will offer a few remarks about our Lytle Lecture speaker, Professor Yann LeCun.
So we are thrilled today to welcome Professor Yann LeCun as our speaker for the 2024 Lytle Lecture. Yann is Vice President and Chief AI Scientist at Meta and the Silver Professor in the Quran Institute of Mathematical Sciences at NYU, where he's also affiliated with the Center for Neuroscience and the Electrical and Computer Engineering Department. He's the founding director of Meta's Fundamental AI Research Lab and of the NYU Center for Data Science. Yann received an electrical engineering diploma from ECE in Paris and a PhD in computer science from the University of Sorbonne. After a postdoc at the University of Toronto, he joined AT&T Bell Labs and then NYU in 2003 as a professor, and he joined Meta in 2013. Yann is best known for his major contributions to deep learning and neural networks, especially convolutional neural networks, which are used very broadly nowadays, for example, in computer vision, in speech recognition, many other places. He is the recipient of the 2018 Turing Award, which is also known as the Nobel Prize of Computing, alongside Jeff Hinton and Yoshua Bengio, for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. Yann is a member of the National Academy of Sciences, the National Academy of Engineering, and the French Académie des Sciences. Most recently, Yann was awarded the French Legion of Honor Medal by President Macron of France. This award is the highest French honor of merit and one of the most prestigious of its kind in the world. There are many awards, so I will not name all of them. He is one of the influential thought leaders of our time, in particular in the field of modern AI. And personally, I'm amazed by not only by his ingenuity, but also by his vision and perseverance that led him to make progress on the topic of neural networks, even when other researchers had given up like a decade ago. So we are very happy to have him today. His lecture will focus on objective-driven AI, proposing a modular cognitive architecture as a path towards developing machines that can learn, reason, and plan. Please join me in welcoming to the stage Professor Yann LeCun.
Thank you, Marianne. Thank you, Eric. Real pleasure to be here. Thank you for coming so numerous. I don't know if it's okay, but you can probably sit on the floor in the front because I see a lot of people in the back who probably can't see much from where they are. Okay. I was about to turn more red than the light. But thank you for the nice introduction. Okay, yeah, so objective-driven AI. Everybody is excited about AI these days, perhaps a little too excited. And a lot of it is because of large language models. And what I'm going to talk about today is where I think AI research should go in the next decade, perhaps. And this is not the only way it could go, obviously, it's just a suggestion. But the main point I want to make is that we're nowhere near solving, getting machines that are as smart as animals, let alone humans. And we still have a lot of work to do. And so if you hear people telling you that AGI is just around the corner, don't believe them for two reasons. First, there is no such thing as AGI. And second, whatever it is not just around the corner. Okay, with that out of the way. Machine learning sucks. I've been working on it all my life, and or professional life certainly. And compared to humans and animals, compared to the kind of learning abilities that we observe in humans and animals, the type of learning paradigms that we have in machines today really don't come anywhere close. So we've gone from supervised learning to like being super excited about reinforcement learning 12 years ago. I never believed in it, but famously. And it's been largely a failure as a way to human-level intelligence. And in the last 5 or 6 years, the excitement has been about self-supervised learning. And that, I think, is a deserved excitement, and I'll say a lot more about that. But animals and humans can learn new tasks extremely quickly. They understand how the world works. They can reason and plan. We don't imagine that simple animals can plan, but in fact they can, like a mouse can plan better than any AI system that we have today. And they have common sense, what we intuitively call common sense. And the behavior of animals is driven by objectives because they have to survive in the world. And I'll say a few words about what that means. Now, there's a lot of people who are excited about AI research, and some of them are really focused on applications of a particular type for healthcare, for material science, physics, whatever, computer vision, transport, autonomous driving, all that stuff. But some of us are interested in really kind of pushing the boundary of AI towards human-level intelligence. And you might think, so first of all, it's a very interesting scientific question, because if we can make machines that are similarly smart as humans and animals, we'll probably learn something about human intelligence, so that's a very important scientific question. It's of course an engineering challenge, but it's also very useful. We need AI systems that have human intelligence. And not because we want them to be autonomous or take over the world, because we want them to assist us. And the best way for them to assist us is to understand everything there is to understand about the world. So there is a future, perhaps not too distant, where every single one of our interactions with the digital world will be mediated by an AI system. It will be with us at all time. This is a picture from the movie Her from 2013 by Spike Jonze. Story of a guy who interacts with an AI assistant and falls in love with it and all that stuff. But those smart glasses already exist. Yeah, you can buy them today, and you can talk to them. They have an LLM in the back, so you can ask them questions. Pretty soon they have cameras, so pretty soon they'll be able to tell you what you're looking at and give you some explanation for what you're looking at if you are in a foreign country. Maybe translate in real time a document that you're looking at. Translate in real time speech to speech if you're in a country where you don't speak the language. And so those things will answer all the questions we have. They will help us in our daily lives. They'll know our preferences and interests. They may surpass us in all kinds of domains of intelligence, but they will be at our service. A bit kind of like having a staff of people working for you, except they're not people. So we need machines that have human-level intelligence, that have common sense, that understand how the world works, that can remember, reason, plan, everything. And they will probably require some level of superhuman intelligence. Certainly, if you want to convince your plumber to come fix your bathroom, you need super intelligence. There's no question about that. And as I said, it would be kind of like having a staff of people working for you. Okay, but we're very far from this. Despite the fact that we have large language models that can pass the bar exam, or can get high score at the SAT or whatever it is, we still don't have systems that can do what a 17-year-old can do, which is to learn to drive in about 20 hours of practice. We still don't have level 5 autonomous driving systems. I mean, we have them, but it's cheating. It's a lot of sensors and mapping and whatnot. Like, how do we get a machine to learn to drive in 20 hours of practice, like every 17-year-old? How do we get a machine to learn to clear up the dinner table and fill up the dishwasher in one shot, which any 10-year-old can do? How do we get a machine to learn to do what a cat can do, like plan a complex trajectory to jump on a piece of furniture? We're nowhere near being able to do this, and it's not because we can't build the robots, it's because we can't get them to be smart enough. So what are we missing? Understanding how the world works. And that will be done with world models, so basically modules that allow the system to understand how the world behaves. And so, we want advanced machine intelligence. So I don't like the phrase AGI, right, with artificial general intelligence, which people have used to designate human-level intelligence system. And I don't like this because human intelligence is nothing anywhere close to general. As humans, we're incredibly specialized. There are certain things we can do, other things that we can apprehend but cannot solve, or not well. You can buy a $30 gadget that will beat you at chess, or certainly beat me at chess. That means you suck at chess, basically. And then there is a very, very, very large collection of problems that we can't even apprehend. Like, we can't even imagine that anybody would solve them. And so we are very specialized. So the whole phrase AGI, artificial general intelligence, makes absolutely no sense to me. So I prefer ami. It sounds like my friend in French, AMI. Okay, so what's the advanced machine intelligence system? It's a system that can learn world models from sensory inputs, learn intuitive physics like babies and young animals. Systems that have persistent memory, that can plan complex actions, and are controllable and safe. And I call this objective-driven architecture. But before I talk about how this could work, let me say a little bit about what really has been at the forefront of progress in AI and machine learning over the last several years, and it's self-supervised learning. That has literally taken over the world. Like, every sophisticated AI system that is sort of being built today uses some form of self-supervised learning. So what's the basic idea of self-supervised learning? Well, there's multiple ways to think about it, but the simplest one, or the most common one perhaps, is self-supervised learning through reconstruction or denoising or prediction. So the basic principle is you take an input, let's say a text, represented by the variable y here on the right, and you corrupt it in some way, or you transform it in some other way. So in this case here, you blank out some of the words, right? So now you have a text with some blank markers in the middle. And you train some gigantic neural net to reconstruct the words that are missing, to fill in the blanks, basically. Okay? And because that system produces the part of the input that are missing is generative, right? It generates the input, it regenerates the input. This model is the basic idea of this kind of model is very old, actually. It goes back to the late 80s, but more formalized more recently, and it's called a denoising autoencoder, right? It's the idea that you have a system that basically takes a piece of data and just reconstructs the piece of data on its input, but the way you train it is with noisy versions of the input. And the reason for doing this is a little complicated. But anyway, so that's what has essentially revolutionized machine learning in some ways, and certainly natural language understanding, and anything that has to do with kind of sequences of discrete objects. Okay, so not just text, but can also be discretized speech, or it can be DNA sequences, protein sequences, things like that. So there's been like astonishing demonstration of how powerful this is in the context of natural language processing and understanding and translation. This is an example, a project that was done by a group of my colleagues at Meta called No Language Left Behind. So this is a translation system that can translate 200 languages in any direction. And what's really interesting about this, and it's pre-trained also using self-supervised learning of the type that I was saying. So basically, this network that is pre-trained has an encoder and a decoder, and in the process of being trained to predict the words that are missing in a text, it elaborates, it learns to represent everything they used to represent about the text, the meaning, the grammar, the style, everything. And the astonishing thing is that you can train those systems with essentially text in hundreds of languages, and will figure out some representation, internal representation of the text that is independent of the language. So what that allows to do is basically train a translation system from any of those 200 languages to any of the other, and any of them, but you only have training samples for 2,400 of the pairs of those 200 languages. It's very sparse, right? You don't have parallel text between rare languages in Africa and India, for example, right? You can play with that system. Most languages only have a relatively small amount of data, but yet those are the 200 languages that it can translate pretty well. Some of them I never heard of. Some of them appear twice because they have two different ways of writing them, and you have to have different translation systems for different writing systems. More recently, so this is a few years old, and more recently there's a version of this called Seamless M4T, which you can play with also at the URL indicated there. That system can handle 100 languages, but what's interesting about it is that it can do text to text, speech to text, text to speech, and speech to speech. And for the speech to speech, it can do this for languages that are not written. So there are a lot of languages in the world that are dialects, and they don't have any writing systems. And that system can actually be used to translate purely spoken languages without going through text, which is pretty cool. There's a version of it also that can translate in real time with about 2-second latency, preserving your voice and the expression. And so those things are going to come to a smart glass, near you soon. And so, language barriers can be erased. In particular, it would allow people who speak rare languages to preserve that language, essentially. What's interesting, before I get into the sort of technical things about this, let me say a little bit also about what are the biggest deployments of machine learning today, or deep learning for that matter, and sophisticated deep learning? It's probably for content ranking and content moderation on various online platforms, particularly social networks. So things like Google, figuring out which search result to show you, YouTube for recommendation, and TikTok, and Amazon, certainly Instagram and Facebook. And you take deep learning out of those systems today, and the companies literally crumble. They're built around it. And it's happened over the last 10 years, essentially. So deep learning there helps us with the deal with the information deluge. And things like translation, text to speech, speech to text, etc., are really important because there are 800 million people in the world who are illiterate, 300 million who are visually impaired, 3 billion people who can't really use technology today. Anyone on Earth except those 3 billion people and 1 billion Chinese are on Facebook, by the way, or on one of Meta's services. If it's not Facebook, it's WhatsApp or Instagram. Anyway, so here is probably one of the most sophisticated use of high-power AI systems today, or at least certainly the most widely deployed, and it's for content moderation. So content moderation is really a complicated problem, and it's necessary on social networks for various reasons, for legal reasons first. Even in the US, despite the existence of the First Amendment, you can't distribute terrorist propaganda or child exploitation or things of that type. And then there are things that are more in a gray zone, like hate speech, how do you define it, etc. But like the most egregious calls to violence, you need to take down, things like that. So let me take the example of hate speech. 95.6%, that was in 2022, of hate speech on Facebook was taken down automatically by AI systems before anybody saw it. This is worldwide. The prevalence of hate speech on Facebook is 0.02%, or 0.01 actually nowadays. So one piece of, one post out of 10,000 is potentially hateful. And then there is all kinds of, unsavory type content also that is being taken down because they're against content policy. And people have been talking about AI in recent years and months as a potential problem because it could be used by badly intentioned people to corrupt the electoral process or rile people against each other and disseminate disinformation. It turns out AI is actually the countermeasure against those things. So AI is kind of the solution to those problems. It's not really the cause of the problem, it's the solution, really. And here is an interesting curve. So in late 2017, the proportion of hate speech that was taken down automatically by AI system was around 23%. Late 2022, it was 95%, and then it dipped a little bit, and now it's back up to 95%. And what caused its progress is self-supervised transformers pre-trained on large data sets in multiple languages, so now we can detect hate speech in every language in the world. Right? So AI really helps, has a big impact for this. Similarly, you can use pre-trained, self-supervised systems to kind of understand the structure of proteins or DNA sequences. In this case, proteins. This is a project that took place at FAIR, which is now a spin-off startup company. ESM Fold, which can produce the structure of 3D structure of proteins and can help design new proteins as well. There's actually kind of famous work on protein folding here at UW in a Baker's lab. But okay, enough for examples of use. What about generative AI and autoregressive large language models? Okay, we talk about LLMs, large language models. We really should call them autoregressive LLMs because that's what they are. So what is it? You take a piece of text and instead of blanking out a number of words and then training a system to reconstruct the words that are missing, you only blank out the last word. Technically, you blank out more, but in the end, what the system is trained to do is just predict the last word in a sequence of words. And once the system has been trained to predict the next word in a sequence, you can, produce that next word, inject it shift it into the input, and then predict the next word. And then shift it and produce the next word, etc. That's autoregressive prediction, not a new concept. And it turns out when you train very large models on enormous amounts of data, of text data, to do this kind of prediction, some emergent property seems to emerge. And the system seem to be capable of understanding a lot more than you would think they are capable of. So that's the magic of self-supervised learning. And those autoregressive LLMs are very fluent. They can generate text that seems really kind of nice and correct, right? And this, for many of you who may not be aware, this does not start with ChatGPT. The first use of neural nets for generating text of this type was actually some work by Yoshua Bengio in the 2000s. And then there was some more recent work and from various groups at Google, at Meta, at OpenAI. And what happened with ChatGPT in November 2022 or October 2022, and what surprised everyone was not the performance of the system, it was the fact that the public got really interested in it. So the type of enthusiasm that the public showed for this system surprised everyone, including OpenAI. And it sort of started a new industry, because before that, people didn't know that there would be kind of a product that you could build out of this that would interest people. So autoregressive LLMs, there's a whole bunch of them now. They output one token after the next. They typically have anywhere between a few billion and a few 100 billion parameters. They're trained on 1 to 2 trillion tokens usually. Now it's more like 10, even more, 10 trillion tokens. And there's a bunch of them that are open. Blunderbot, Galactica, Llama 1, Llama 2, Code Llama, Mistral, Falcon, Alpaca, Yi, etc. There's a bunch of them. Some from Meta, some from other people. And then a bunch of proprietary ones. Meta AI, which is built on top of Llama 2. Lambda and Bard from Google, Chinchilla from DeepMind, which is an experimental system, and ChatGPT for OpenAI. Okay, performance is really amazing, but they make really stupid mistakes. Those systems hallucinate. They produce text that sounds fluent, but maybe completely false, factually. And so people have come up with tricks to kind of augment the text generation by looking up a knowledge base or a search engine or something like this. That's called RAG, Retrieval Augmented Generation. And it's kind of a trick to kind of get those systems to be more factual. But they certainly don't have any common sense. They can't plan. They don't understand the physical world, etc. You can play with them, of course. There is some of them that you can play with on Facebook and Messenger and WhatsApp and whatever. But here is a major issue with them. Because they are autoregressive, if you think that there is some sort of probability for any token to take you out of the set of acceptable answers, the probability that the system will stay within the set of correct answers has to decrease exponentially if you assume the errors are independent, which of course they're not. But so there is an intrinsic limitation of this kind of autoregressive prediction. And we don't do this when we speak. We don't just dream up one word after the other. We sort of plan our answer, more or less. And there's some interesting work actually along those lines about the possibility of getting LLMs to plan, among others by Ye-Jin Choi, who is here. So autoregressive generation really sucks. A lot of things sucks in machine learning. I wrote this paper a while back with a young colleague, Jake Browning, who's a philosopher. It's a philosophy paper on the limitations of training AI systems from language. And a bunch of people coming from sort of the more traditional branch of AI, sort of non-deep learning, pre-deep learning days, if you want, have been writing papers about the fact that LLMs basically can't plan. They can't do search. They can't do real reasoning. This is by Subbarao Kambhampati, who's has been publishing a bunch of papers on this. One of them is by MIT, a group of cognitive scientists at MIT. So they really are not good for anything. And so the idea that somehow we're going to scale those up, I mean, they're very useful, but they're not good for reaching human level intelligence. So the idea we're going to scale those up and train them on even more text, which we don't have because basically they're already trained on the entirety of the public text on the internet. The idea somehow we're going to scale them up and reach human intelligence is nuts. It can't possibly work. So AGI is not around the corner, if you believe in AGI. And so we're easily fooled by their fluency into thinking that they are smart, but they really aren't. They're useful, there's no question. We can build an entire industry around them, okay? And more power to the people doing this. They're going to make our search engines better and everything better, writing aids, everything. So we're not going to get to human level intelligence by just scaling up LLMs. And the question is, what do we miss? What are we missing? But let me say it, there is absolutely no question in my mind that eventually machines will surpass human intelligence in all domains. And this may happen within the lifetime of a bunch of people in this room, perhaps not me, I'm not sure, but it's not very far in the future. It's not right around the corner, but it's not very far in the future. There's no question this will happen. Okay, so we're missing something really big, and what is it? What is it that allows a 10-year-old to learn to clear up the dinner table in 10 minutes, or in one shot, or a 17-year-old to learn to drive in 20 hours, or a house cat to plan complex action sequences to jump on a piece of furniture? And why is it that we have systems that appear to be smart, but then really aren't that smart? It's Moravec's paradox. It's an old story about computer science that things that seem to be complicated for humans, like solving integrals and playing chess and Go and stuff like that, are actually easy for machines and vice versa. But okay, here is why perhaps we're doing all of this wrong. Why LLMs will never get to where we want. So typical LLM today is trained on 10 trillion tokens, 10 to the 13th. Each token is about 0.75 word. You can sort of evaluate it this way, and each token is about 2 bytes. In the typical tokenization of language, you have 30,000 possible tokens, so that's 2 bytes, right? So do the math, that's 2 10 to the 13 bytes. That's the size of the training set used to train the latest LLMs. It would take 170,000 years for any human to read through this at reading 8 hours a day at 250 words per minute. That's an enormous amount of information, right? Well, not really, because if you take a human child, a 4-year-old has been awake 16,000 hours, and you try to quantify how much information has gotten to the visual cortex of that 4-year-old in his or her life. You got 1 million fiber in each optical nerve. Each optical fiber carries maybe 10 bytes per second, so that's 20 megabytes per second. Multiply by 16,000 hours, multiplied by 3,600 seconds per hour, and a 4-year-old child has seen 10 to the 15 bytes. That's 50 times more than the biggest LLMs in the world in 4 years. So what that tells you is that we're not going to reach anywhere close to human or even animal intelligence by just training from text. We've already saturated the amount of text that we can train on. 10 trillion token, that's basically the entire public internet. And we're seeing already the performance of those LLMs kind of saturating. We're not going to get much better than currently without using sensory data, high bandwidth sensory data like video or images. So that's what we need to do, get machines that, learn to represent the world and have predictive models of it, learn to reason and plan. If you know about Daniel Kahneman's System 1, System 2, our current AI systems can do System 1, but not System 2, and learning to plan. How are we going to do that? Okay, so here's an idea. It's not the panacea, and I can't exhibit a system that actually does what I'm going to describe, but this is perhaps a possible path towards kind of solving the problem I was just talking about. So I published this paper a year and a half ago called A Path Towards Autonomous Machine Intelligence. I replaced autonomous now by advanced because autonomous sounds scary. And it's on open review, it's not on archive, because on open review you can comment. And the basic idea here is some sort of what people used to call in the old days a cognitive architecture. So basically a modular system composed of multiple modules. So each module, think of each module as some big neural net. And each arrow carries signals forwards, but also carry gradients backwards, okay? So think of this as kind of a big neural net macro architecture, and you can backpropagate gradient to the entire thing. So the red stuff at the bottom is a set of cost functions, and those only have arrows coming into them. They compute a cost, and then you can compute gradients of this cost with respect to all the parameters in the system by backpropagating along the other arrows. Okay, so what's happening? The system observes the world. The world goes into the perception that gives an idea of the current state of the world, perhaps combined with a memory. That goes into a world model whose role is to predict what's going to happen if you take a particular sequence of actions. The actor imagines a sequence of action and then uses the world model to predict what's going to happen. And then that goes into the cost module, which evaluates whether the outcome of this sequence of actions predicted by the world model is good or bad. Okay? And you can propagate gradients or whatever so that the actor can optimize its sequence of actions so as to satisfy the goal. So if I draw this in a way that's slightly more understandable, it looks like this. Okay? Observe the world, go to the perception system. Perception system figures out some representation of the state of the world, combined with memory, which perhaps has some previous information acquired about the state of the world. Goes into the world model. The world model also takes the action sequence, an imagined action sequence, and predicts the outcome of taking this action sequence given the initial state of the world. And that goes into different terms of the cost function, a task objective that measures to what extent the outcome satisfies the goal that the system was given, the objective. And then perhaps a bunch of other costs that are guardrails. So things that guarantee that whatever action the system takes are not going to kill anyone or destroy the machine or whatever, right? Guardrail objectives. And the way the system operates is that through some optimization process, it tries to figure out what action sequence will optimize those guardrails given that the world model is predicting the outcome. Okay, so that's an optimization process. So this is fundamentally different from what we usually do with neural nets, which is we run through a bunch of layers and we outcome an output, right? There's a finite number of steps to produce the output, a given number of steps. Here, the output is produced by optimization. This is not a new concept at all. This is the way inference works in probabilistic models, in latent variable models, in graphical models, probabilistic graphical models, things of that type. That's the way it works. You know certain variables, and then you infer the value of the variables you don't know, or distribution over those variables. It's the same thing here. You observe the state of the world, and then by optimization, you infer a sequence of actions that minimize a set of objectives or maximize some negative some likelihood or log likelihood or whatever. So that's objective-driven AI, okay? Now, everything remains to be done, which is how do we train this world model? How do we do the optimization algorithm? How do we train the perception model? How do we design the cost, etc.? Now, the world model may be an incremental world model. So something that says, here is the state of the world at time t. Here is the action I might take. What is going to be the state of the world at time t plus 1? And of course, I might want to run this multiple time steps, right, to predict what's going to happen after multiple actions, etc. So you can sort of have an unworld version of the previous model I explained, where you run the world model multiple times for each action or group of actions that you're taking. You may have guardrail costs for every time step, and then a task cost at the end. Now, unfortunately, the world is not entirely predictable. It may be deterministic, but it's not predictable. So this world model has to take into account some latent variables that basically represent what you don't know about the world. And those latent variables will have to be drawn from some distribution or swiped over some set, so that for every action here, you might have a whole set of predictions that correspond to the various settings of those latent variables. Okay, and it's not trivial how to do this. But ultimately, you want something a bit more sophisticated than this, because when we plan action sequences, we don't plan them at one level. We do hierarchical planning. So what's hierarchical planning? Basically, imagine a two-layer system of this type, or multiple layers, but a system of this type where you have an ultimate task objective, and the representation of the world here goes through not just one encoder, but two successive encoders that produce a very abstract representation of the state of the world, which may eliminate a lot of details about the state of the world. And then you plan a high-level sequence of actions represented by those latent variables, because they're not really actions, they are more like imaginary concepts. And you plan those two variables so that the task objective is minimized, and what that does is that produces an intermediate state here that you can use as a desired state for the level below to now plan. So that's like a sub-goal determined by the high-level system. And that sub-goal now can be fulfilled by the lower level, which maybe itself is a function of elementary actions. Let me give you an example to kind of make this a little clearer. Let's say I'm sitting in my office at NYU in New York, and I want to go to Paris. So my cost function is my distance to Paris. And obviously, there's two actions I can take successively. The first one is catch a taxi to go to the airport, and the second one is catch an airplane. And I have choices of exactly how I do this. But okay, the first thing I need to do is catch a taxi to the airport. How do I catch a taxi to the airport? That's my distance to the airport. That's my new cost now for the sub-goal. First thing I need to do is get down in the street and hail a taxi. How do I get down in the street? I have to go to the elevator, take the elevator down, go down in the street. How do I get to the elevator? I have to raise from my chair, open the door of my office, pick up my bag, blah, blah, blah. How do I get up from my chair? I have to kind of plan all of this in terms of millisecond by millisecond muscle control, but I'm not going to plan my entire trip to Paris in terms of millisecond by millisecond muscle control. It's impossible, right? So we need this idea of hierarchical planning. I tell you, nobody today knows how to do this. There's no AI system that is capable of doing this other than by designing those layers, those intermediate representations by hand. So robotics, for example, planning to get a walking robot to go from one part of a room to another part. There is some high-level planning, which is like, what path am I going to follow? And the low-level planning, which is like, how do I move my legs? Okay, but that's designed that's handcrafted, hardwired. How do we get a system to learn those intermediate abstract representation layers so it can learn to do hierarchical planning? We have no idea how to do this. Super interesting problem, very challenging. If you work on this, you're not going to be in competition with people training LLMs on 8,000 GPUs. All right, that's the good news if you are in academia. So that's a big challenge. If you're a student looking for a PhD topic, I want to. Okay, but now next problem: how do we get machines to learn those world models? Okay, because they need to do that, and we're going to need them to use self-supervised learning. So this chart comes from Emmanuel Dupoux. He's a cognitive scientist in Paris, also affiliated with FAIR in Paris, and he made this chart that indicates at what age babies learn basic concepts like the distinguishing animate from inanimate object or object permanence, the fact that when an object is hidden behind another one, it still exists. Things like stability, rigidity, natural categories of objects. Babies and certainly animals don't know the names of objects, but they have some concept of categories. And then things like gravity, inertia, conservation of momentum, basically what we could call intuitive physics, that only pops up around 9 months. So a 6-month-old child that sees a little car pushed off of a platform that appears to float in the air, no surprise. A 10-month-old baby goes like this. because in the meantime, the baby has learned that objects that are not supported are supposed to fall, and so that violates, the internal mental model, right? So how do we learn all this? Okay, maybe we can use self-supervised learning for this, and perhaps the idea would be to use the same kind of model I was suggesting earlier. One model really, as I said, is a system that, given the state of the world at time t, can predict the state of the world at time t plus 1, given a imagined action that the agent could take. Okay, so perhaps the way to do this is to take a piece of video and then masking the latter part of it, for example, so that the system only sees the beginning of the video. And then it's given perhaps an action that a character in the video is taking or whatever, or some transformation. And then you train the system to predict what's going to happen in the future of that video, right? And if the system can do a good job at predicting what's happening in the future in the video, it probably has captured the nature of the world, right? It knows that certain objects can move in certain ways and not others, and the world is three-dimensional, and blah, 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 right? And what it will have as a result of this is some sort of causal model of what action can be taken to turn a particular state of the world into another particular state of the world, at least in this representation, or what can follow a particular piece of video can be generated. Sounds great, right? Doesn't work. Here's what happens. You get blurry predictions. Okay, so here it's a small animation with 6 frames. The first 4 frames are observed, and then the last 2 frames are predicted. And the 2 frames that are predicted are incredibly blurry. Why is it? It's because the system just cannot predict exactly what's going to happen next, and so it predicts the average of all the possible things that can happen, and that's a blurry image. And the representations that are learned by the system are terrible. Like, you can't use them for anything. So this was in 2016. Since then, we've made a little bit of progress. We have like a system that can make more definite, not blurry prediction using a GAN-like method or variational autoencoder kind of method with latent variables, but still not completely satisfactory. And I was really kind of stumped by this problem until about 3 or 4 years ago. And the solution is something else. The solution is what I call joint embedding predictive architecture. And here is the punchline. It's not a punchline, but here is an interesting thing about it. It is not generative. Okay, so everybody is talking about generative AI. The future of AI is not generative. So what's a joint embedding architecture? It's basically very similar to what I showed you earlier, except you take this Y variable and you run it through an encoder. Okay, so you take the Y variable, which is the full observation, run it through an encoder, corrupt it, transform it, whatever. Now you get the corrupted or masked version of it, or transformed version, run it through the same encoder, possibly. And then you have a predictor, and what the predictor predicts is not the pixels of the video, but an abstract representation of those pixels as produced by the encoder. Okay? And also the system takes into account the action, if there is one. Okay, so it's joint embedding because you're embedding the 2 inputs using encoders, producing embeddings. And then you do the prediction in embedding space, and the cost function, the prediction error, if you want, is in representation space, not in pixel space. Now, what does that buy you? It buys you the fact that now you don't have to reconstruct every single detail of the input. You can represent an abstract representation of the input that eliminates all the stuff that you can't predict. So if I take an object, let's say this water bottle, and I put it here, and I let it go, you probably can tell that it's not going to stay there. It's probably going to fall. You might not be able to predict if it's going to fall this way or that way. So if you want to predict, you don't want to be predicting exactly all the details of this image, but what you would like to predict is some abstract representation of the bottle being up or the bottle being fallen, essentially, right? Eliminating the details that you can't predict. If you have a car driving around the road and you want some predictive model of what the cars around it are going to do so you can drive safely, there's going to be a lot of details about the scene that you don't want to predict. Perhaps it's a windy day, and there is trees bordering the road, and the leaves are moving, you're not going to spend any resources predicting the motion of the leaves. That doesn't make any sense, right? So what you want is make prediction in abstract representation space, and that's the whole idea of this joint embedding predictive architecture, JEPA. So that's the difference, right, between a generative architecture that reproduces the input and joint embedding that produces a representation of the input. Bigger, huge advantage in this one if you can make it work. Now there's several flavors of this. There's an old version of this that we used to call Siamese neural nets, joint embedding architecture. A version where you have a predictor, and then a version where you have a predictor with an action or latent variable. So that's a JEPA, a full JEPA, that's a deterministic JEPA, and that's a JEA, joint embedding architecture, or a Siamese network if you force those two encoders to be identical. And this can handle uncertainty in the prediction. If you have a latent variable that can vary over a set, then the prediction will also vary over a set that is parameterized by this latent variable. So you can handle uncertainty. I'm not insisting that those models be probabilistic, and in fact, I think it's not useful to view them as probabilistic. It sort of makes everything more complicated. And for that, I have another framework that I call energy-based model. You can think of it as kind of a weaker version of probabilistic modeling. And what's an energy-based model? An energy-based model is basically a function of with scalar outputs that measures the degree of incompatibility between two variables. So if you have two variables, y and x, you feed y and x to this function, and it gives you a low number if x and y are compatible, and a large number if x and y are not compatible. Okay? You can have actually only one variable, y. If it's consistent, you get a low number. If it's inconsistent, you get a high number. I call this energy because that's like the log of the negative log of some probability, except it doesn't need to be normalized, which is a huge advantage. Okay, so what does that mean? Let's say you have data. Let's say y and x are scalar variables, and your data points are those black dots. Okay, so there is obviously a dependency between x and y. It's not a functional dependency, but there is a dependency. For any particular value of x, there is a number of possible values for y, or might be blurry, but it doesn't matter. So the way you capture those dependencies is through this energy function that takes low value on the data points and nearby, and then higher values outside, and you can think of this as being sort of level sets. And so the question is, how do you train an energy-based model? So this is more general than probabilistic models, okay? But weaker in the framework. So here's the problem. If this energy surface is infinitely flexible, and the only thing you do is try to change the parameters of this energy function so that it gives low energy to your training samples, it could very well collapse. The collapse means that basically every data point in your space has the same energy. So the system has not captured the dependency between the variables because it gives the same energy to everything. So you have two sets of methods to make this work. One set is contrastive methods. Contrastive method consists in generating fake points outside the manifold of data, basically, and push their energy up while you push down the energy of the data points. Okay? And then you have other methods, regularized methods, and those methods basically, what they try to do is minimize the volume of space that can take low energy, so that when you push down the energy of data points, the rest has to go up because there's only a finite amount of volume that can have low energy, right? So those two categories of method. Let's say we start with a training set represented by those data points, and our initial energy function has low energy within this region here, so it's not a very good model of the data. Think of this as a level set. In contrastive method, you would generate those green points and then push their energy up while you push down the energy of the data points. Okay, so eventually the system might take the right shape. There's a major issue with this, which is that in high dimension, the number of contrasted samples you're going to have to generate to push up the energy of everything you don't want grows exponentially with dimension. That's bad. Okay, so a priori that's not going to be super successful, but it's actually quite popular at the moment, those contrastive methods. And then the other ones are regularized methods. So regularized methods basically try to minimize the volume of stuff that can take low energy, so that when you push down the energy of the regions you want around the data points, the rest has to go up because because they have to with this regularizer. Okay, so my recommendations are work on planning and reasoning and memory, but abandon generative models, abandon probabilistic models in favor of energy-based models, abandon contrastive methods in favor of those regularized methods, and of course abandon reinforcement learning, but that, okay, so all the popular stuff at the moment in machine learning, I'm telling you, like, if you want to reach human level intelligence, you should forget about them. I'm being almost as controversial as Pedro. That's hard, no? No way. Okay, so here's the problem. How do you train those JEPA architectures? And the main issue that you have to deal with here is this collapse problem I was telling you about. So if you're not careful and you train those architectures, you have a bunch of data, X and Y, you train the system to just minimize the prediction error in representation space, it doesn't work, the system collapses. What it does is that it ignores X and Y, it produces SX and SY that are constant, and so now the prediction problem becomes trivial and your prediction error is 0, and the system hasn't learned anything useful. That's a collapse of the type that I was mentioning before. The energy is 0 for everything. Okay? How do you prevent this from happening? In the case of this architecture, the way to minimize the volume of stuff that can take low energy is that you maximize the information content that comes out of SX and SY. So this block here is like a cost function you're going to minimize during training. And it's a negative information content, if you want, some estimation of information content. So we're going to try to maximize the information content of what comes out of those encoders while we minimize the prediction error. Forget about this for now. Okay, so the first thing you should do to maximize the information content is ensure that those variables, when they come out of the encoder, are not constant. If they're constant, they don't carry any information, right? So what we're going to do is measure the variance, or the standard deviation, rather, of each of the variables in the vector Sx, and have a cost function here that makes sure those standard deviations are above 1, or some arbitrary number. That's a hinge loss that forces the standard deviations to be above 1. But that's not enough. It's not enough because the system can choose to make all those variables pretty much equal. And so the information, the content of it is very low. So the second criterion is take the covariance matrix of individual variables coming out of Sx over a batch, measured over a batch, and make sure the off-diagonal terms of the covariance matrix are as close to 0 as possible so that the variables are uncorrelated. Okay. And you would think that's enough. So basically, the combination of those two things says the covariance matrix of this vector coming out of this encoder measured over a batch should be pretty close to the identity matrix. And there is a bunch of different algorithms that have proposed this relatively independently, one by Yima, that he calls MCR squared, and then one that we proposed called VicReg, and then the predecessor to VicReg also came out of my lab at Meta called Barlow twins. But in fact, you can use another trick, and the other trick is making variables uncorrelated is not sufficient. You really want to make them independent. And it turns out you can do this to some extent by feeding that vector into another neural net that expands the dimension. So the vector that you're going to have here is higher dimension than Sx. And you're going to decorrelate the component of that vector, and this will have the effect of making the components of this vector more independent. Not completely independent, but more independent. Okay, so what I told you is kind of a hack to maximize the information content of a bunch of vectors coming out of an encoder. But here's the trick here. What I didn't tell you is that what we are maximizing here is actually an upper bound on information content. Okay, so we have an upper bound on information content, which is this covariance matrix. The real information content is actually lower, and we're pushing up on this upper bound, and we're crossing our finger that the actual information is going to follow, right? So it's a hack. It's not completely justified, but that's the best thing we have. If you have a nice lower bound that we can compute of information content, talk to me. Okay, so how do you use this system? How do you test whether they work, right? So one scenario is you take one image, you distort it in some way, transform it and distort it and corrupt it in some way, run it through two identical encoders, and then try to make the two representations identical. So this is more an architecture of this type. Take an image, transform it, run it through encoders, forget about this for now, and try to make the representations coming out of the encoders as similar to each other as possible. And the reason you want them similar is because you know that this is the same content. This is the same image, really. It's two views of the same image. Maximize the information content so the thing doesn't collapse. And once the system is trained, chop off the last couple layers maybe of that system, or sometimes not, and then take the internal representation that has been learned by the system, feed it to a linear classifier or some other classifier that you train, supervise, and measure the performance of this on some image recognition task like ImageNet. And this works. And in fact, it's the only thing that really works. Like in self-supervised learning for images, the method that employ reconstructions don't work. So you can use VAE, you can use GANs, you can use masked autoencoder, MAE, came out also of FAIR, things like that. The features you get are really bad. The only thing that really gives you good features for images are the joint embedding architectures. But there's a whole bunch of different methods on how to do this. I only described like one class. There's a whole bunch of them. There's BYOL from DeepMind, there's Obo from a lab in France, there is SimSam, Suave, Moco. SimClear is a contrastive method. And some going back to 4 years ago. And then Barlow Twins and VicReg are the ones I explained. And then there is a more recent one called Dino, which is very similar, which I'll talk about in a second. So this works. It can be extended to train system, not to just recognize objects, but to do like image segmentation and work with like large transformations from one image to another. But let me not go into those details. Some of the stuff that works too is very well is distillation methods. So distillation methods are methods where the two encoders are not exactly identical. The weights of one of the encoders are basically a sort of exponential moving average of the weights of the other encoder. And you don't backpropagate gradient to this encoder. You only backpropagate gradient to that one. And again, you have a cost. You may have a predictor in between. So one such method is SimSiam, BYOL from DeepMind, SimSiam from FAIR, California, and Dino V2 from Paris, FAIR Paris. This works really well. If you want a completely like pre-trained feature extractor that is generic today, just get Dino V2. That works really well. It produces, and you can play with a demo or download the code and play with it. This is trained using one of those distillation methods in self-supervised mode. It's using a quantized output. I'm not going to go into the details of how this works exactly. This is some visualization of the features that are extracted from all kinds of images. Doesn't tell you much, but it works really well. This is the first author's dog. And that's kind of the features, a visual representation of the first three principal components of the feature vector that are extracted from every region. Now, what's interesting is that you can use those features not just for segmentation or recognition, but also for depth estimation and all kinds of stuff. So they're really generic features. In fact, a group at FAIR Paris used this to estimate the height of the canopy in a forest from satellite images for the entire world. And you don't need to train it with much because it's pre-trained to extract features that are fairly generic. So you just fine-tune a head. You train a head on top of Dino with like a small area for which you have the height of the canopy from radar or something like this. And then you just apply it to the entire world and you get the height of the canopy, and that gives you an estimation of how much carbon is captured in forests. This is a more recent algorithm called IJEPA, ImageJEPA. And it's again a distillation model. The only difference with Dino is that it doesn't use quantized representation and it has a predictor. It's very minor differences, but it works really well and it trains really fast. And so we can get like really top performance on object recognition tasks with this method and really quickly. It works much better than things like masked autoencoder that you may have heard of in terms of performance and speed and training speed as well. And it produces better results with a frozen trunk, which mass autoencoder requires fine-tuning the trunk. I don't want to bore you with all the numbers, so let me skip ahead. Yeah, you can read the papers. This I'm going to skip. Okay, so coming to the end a little bit, we have a bunch of problems to solve to kind of get this to the next level and really build intelligent systems out of those ideas. It's going to take a while. This is not going to be happening over the next year. It's going to take several years. So we need to be able to train JPAs with regularized latent variables to handle non-deterministic environments, figure out planning algorithms in the presence of uncertainty that work with what the kind of architecture I described. We need to learn the cost modules. This is what some people have called inverse reinforcement learning for reasons I'm not going to explain. We need those systems to be able to plan with inaccurate world model, and that's kind of a major failure mode that can occur with those systems. So a lot of kind of problems to solve. This is not completely solved. And we're working on various aspects of this. So self-supervised learning from video. Basically, we have a video version of iJEPA, and I can't tell you the results yet. And then use those world models inside of systems that can reason plan and are driven by objectives, which will make them not hallucinate because they plan their answer instead of kind of just producing one word after the other. They'll have guardrails that will allow us to control their behavior. And then the problem of learning hierarchical planning, and that's still very complicated. So a number of different points. Computing power is going to be important. You may have seen an announcement that Meta is going to have something like 600,000 GPUs by the end of the year. This is true. Each GPU, H100, costs a couple tens of thousands of dollars, so do the math. So what's funny about this is that there were articles in the press until recently of Meta being stupid because Meta was losing $30 billion a year in building the metaverse and augmented reality, virtual reality. In fact, most of this money was spent buying GPUs, and now we look like geniuses. Because you can get those things, even if you have the money. So we're still missing essential concepts to reach human-level AI. I made one proposal, maybe you have better ones. Making those objective-driven architecture work in the end is going to be a little complicated and difficult. But in the future, we'll have those universal virtual assistants that will live in our augmented reality glasses or smart glasses or smart devices, whatever they are. But then what that means is every single one of our interaction with the digital world will be mediated by one of those AI systems. They will basically constitute the repository of all human knowledge, okay? And all culture, all languages, all value systems, everything. Now, because it's so expensive to train a large foundation model of this type, you don't want 50 companies to build 50 of them. You just want a few that are basic ones, and then you build on top of them. If you think about the software infrastructure of the internet, which is today runs on Linux, right? Every server on the internet basically runs Linux. Even most phones run Linux, except the iPhones, but who cares? No, really, it's a small minority of phones. And it's a variant of Unix. It's a different brand, but yeah. The point is, when something is shared infrastructure, it wants to be open source. There is a demand from the market to make it open source because it's the only way to make it safe and controllable and customizable and blah, 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 right? So if your car has a computer, it probably runs Linux. And the Mars rover and the Mars helicopter run Linux. So AI systems will become common infrastructure, and we'll need them to be open source for that reason, so that they are safe in various ways. But they will have to be open source for another reason. And that reason is that we can't have a single one or even just a few of those systems being built on the west coast of the US by by companies that release proprietary versions of it. Because how are they going to take into account the diversity of cultures, languages, and values around the world? It's just not possible. And so we need open source basic AI systems that then can be customized, fine-tuned, retrained by interest groups, linguistic and cultural groups, etc. So we have a diversity of AI systems we can interact with. So having diverse AI platforms that basically feeds our digital diet to us is as necessary as having a diverse set of news outlets, right? If you tell the French government, and I know because I told them, the French president, as a matter of fact, do you want your citizen to get their entire digital diet through a proprietary system built in California? And the answer is absolutely not. That's completely unacceptable. Like, they're not going to take into account, our language and our culture, first of all. And second of all, what about political values that are built into the systems, which are baked into the training data that they're trained on? They may not agree with us. We need diverse source for the same reason we need a diverse press. So that's the necessity of open source platforms. Getting AI systems, proprietary AI systems from the West Coast is actually not the worst case. The worst case is getting them from China. And so I've been pushing for open source AI platforms for that reason. Now, the counter argument against that is that if you open source powerful AI technology, bad guys can put their hands on it and maybe do bad things. Yeah, that's true for every technology. But as I said before, AI technology is also the best countermeasure against bad actors. So platforms, foundation models will need to be open. Training and fine-tuning will be crowdsourced with diversity of people, kind of like Wikipedia a little bit, but maybe even more diverse because Wikipedia is so particularly diverse. And then proprietary systems will be built with vertical application on top of that, and so that everyone has the assistant they want and they need. That will require massive computing infrastructure for inference. And in fact, most of those GPUs that Meta has been buying is not for research or training, it's for running AI systems, serving billions of people who want to talk to chatbots. How long is it going to take to reach human-level AI? Almost certainly longer than you think. Okay, because that's been a constant over the entire history of AI, that a community came up with a new way of approaching AI and all of a sudden said, that's it, that's the solution, we're going to reach human-level AI within 10 years. And every single time it was wrong. It's true today too. The people who tell you AGI is around the corner are wrong. And before we get to human-level AI, we're going to have to get through cat level and dog level and stuff like that. I'd be happy if, by the time I retire, which is coming fast, we get to this point. There's no such thing as general intelligence, as I said. No question we're going to reach and surpass human intelligence with machines at some point. Might take a while. But intelligence really is a collection of skills and an ability to learn new skills really quickly. And it's not a linear thing that you can measure with one scale or number. Okay, so there's short-term and long-term risks attached to AI. The short-term ones are things like disinformation, whatever. AI is part of the solution for this, but there is a bunch of important elections coming up in the world, and this problem is not entirely solved. I don't think it's going to be as much as a problem that people imagine it is, but it's still a serious problem. There are long-term risks, things like superhuman level AI that is going to take over the world. That's not happening. It's not happening because it's not because the system is intelligent that it wants to control or dominate. It's not even true of humans. It's not the smartest among us that want to be the chief, right? It's certainly not true in politics. So intelligence is not correlated with the desire to dominate. It's probably inversely correlated, actually, in humans. Like, we all know the smartest people in the world that the world never heard of because they are like recluse and, solving incredibly complex math problems that we don't understand, but they don't want to talk to anybody. So objective-driven AI architectures will make AI systems subservient to humans because we set the goals for them, and they cannot escape the goals that we set for them. They are hardwired to satisfy those goals, which is not the case for autoregressive LLMs. Autoregressive LLMs have no goals. And so AI system would not be a species that we're competing with us. I mean, people have been talking about this. It's just completely realistic. So the doomers are wrong. The speculation about probability of human extinction is complete speculation. There is an infinite way of building dangerous and unreliable AI systems, or any piece of technology for that matter. But the only thing we need is one right way to do it, to be safe. There is, all of us here, I mean, I don't know if there are any aeronautic engineers here, but like, we could try to build a turbojet. Like, most of us would probably fail. Most of our turbojets will either not run or blow up. But there is a proper way to build turbojets so that you can fly 15 hours in an airliner with 2 engines, in complete safety. So it doesn't matter that there is tons and tons of ways to make turbojets dangerous. There's at least one way to make it safe, and that's all we need. Same for AI. You can have all kinds of scenarios that imagine that AI is going to kill us all, but it's not going to happen if we have one scenario in which it doesn't happen. Okay, so that's it. And the idea somehow that if you make the slightest mistake, then humanity is doomed. That's just ridiculous. So building and developing safe and reliable AI system will take a while. But once we do this, this will amplify human intelligence. Every one of us would be a boss of a staff of smart virtual people working for us. This will amplify human intelligence as a whole. And this may bring a new era of enlightenment for humanity if we do it right. A new kind of renaissance, kind of similar effect as the invention of the printing press in the 15th century. Thank you very much.
Thank you, Professor LeCun, for this excellent talk. So we have some time for questions. There will be 2 standing microphones in the room, and if you have a question, please walk up to the microphone. One is in the center, microphone 1, and on the edge aisle, there's another one, microphone 2. Feel free to line up, and we'll call on which microphone to ask their question. We request that you keep your questions short and concise if possible, and just ask one question. Thank you. Okay, we can start with microphone 1. Please go ahead.
Thank you for it. I had a question about ChatGPT and your hallucinations that it has. It seems to hallucinate references, which as a reviewer of scientific journals is really a good way to tell which ones were written by ChatGPT. Is the tendency to hallucinate references and just make them up, is that a fundamental problem or is that a trivial problem?
The relatively simple solution is this RAG method, retrieval augmented generation, which consists in basically encoding a question and then indexing into a vector database or something like this, a knowledge base of some kind, or a search engine, and then inserting the factually correct answer in the prompt, and then having the system just turn this into fluent text, right? So, and there's a bunch of systems that work this way. Some of them are already kind of commercial products, like Perplexity.ai is a search engine that kind of does that. The chatbots that Meta is producing do this also with search engine. So it can be fixed, but it's only kind of a mitigation. Ultimately, I think you want systems that plan their answer of the type that I described, but I can't give you an example of this working. But I tell you, people at Meta, OpenAI, and Google at least are working on planning methods. That's really the hot thing at the moment.
Yes, microphone 2.
Okay, is this okay? Yeah, first, thank you, Yann, for visiting our school. It means so much to us. My question is, so I'm concerned about the consequences of mass data collection, both on people's safety and the environment. Do you think that state-of-the-art solutions in AI are going to always rely on more data, more resources, more computation, or do you ever foresee a shift happening towards maximizing learning with limited data sets or more efficient learning?
Yeah, so everybody wants to have systems that are more efficient in terms of their data use. So there is a huge incentive already. There's also a huge incentive to make them cheaper computationally and to make the hardware more efficient computationally. So you don't need to like complain about people not being interested enough about this. Like there's enormous incentive, economic incentive for both of those things. So it's happening as fast as it can happen. If you can reduce the number of GPUs that are required for training or inference, right? You save a lot of money. If you reduce the power that they consume, you save a lot of money. If you reduce the amount of data you need to collect, you also save a lot of trouble. So those things are being worked on. Like there's enormous teams in all the big companies working on this. And the better news, perhaps, is that possibly with the type of methods that I described, the amount of data that would be necessary to get systems to get to a decent level of intelligence would not be as large as the current ones. That's the hope. Like babies learn to speak with like a remarkably small amount of exposure to language. We're far from that yet, but I think that may happen. Computation, on the other hand, is going to keep growing. So the growth of the amount of computation that is spent to train AI systems is actually pretty constant because it's limited by economics. So that doesn't grow exponentially. The amount of computation grows exponentially, but it's just because the hardware is becoming exponentially more efficient, right?
So to maximize a lower bound on the information, why not just learn a mixture model?
I'm not sure I see the...
Well, the mixture, right, the light model is bound on the information, right? And the mixture model ignores dependencies, right? Components, if you have infinite components, you have all the information, and you can have as many as you want.
Right, okay. So then we're getting into the debate of like, how do you, is there an objective way to estimate information content? And my answer to this is probably no. Like every measure of information is relative to a particular model. So I think if you use a mixture model, you'll get one particular set of estimate, which probably will work in relatively low dimension. But like, gas and mixture or like RBF kernels or things like this, like they're not really good in high dimension because basically every data point is an island.
Well, the reward is really what you care about. So task relevant information.
The reward?
Yeah, task relevant information, right? Maximize the task relevant information.
Yeah, but the problem is you want to learn generic representations, right? You don't want them to be dependent upon a particular task. So there's no reward when you train the word model.
There's a universe of tasks. There's no such thing as AGI. But anyway.
Yeah, okay.
Check. I'm curious with how you train world models, right? You spoke about like text not being like the thing that you train on. So if you take modalities like images that represent our world, how does that train a model? Is that like at the end that would also be taken down into like a text description of it that predicts the next version of it? So I'm just curious like how you train for multiple modalities that isn't like at the base just text that's predicting the next token for it.
No, it's not text. No, I'm not talking about textual representation of anything. In fact, what I've been arguing for is the fact that you don't want to go through text. Text is a terrible representation of knowledge. Like, I mean, the kind of manipulation you do in your mind when you think about, like, I don't know, building something out of wood or something, that has nothing to do with language. It's not connected with language. Anything that any animal does has nothing to do with language, at least for most animals.
So
right?
How do you like take the modality to like, so if I'm thinking in images, how do you make a system think in images to think of the next action then if it doesn't go down to text?
Well, so that's the idea of this JEPA architecture, right? You train the system to produce a representation within which it can do prediction. Like given an action, what's going to be the next state of the world. And that doesn't have to have any relation to text or language, right? It's just some abstract representation of the state of the world.
So is it just like diffusion engines like predicting the next state of a system then in a visual representation?
Well, I think you might have in your mind like an idea of a system that in the end produces text. Like I'm not thinking about this, I'm thinking about a situation where perhaps the sequence of actions the system will take would be producing words, but perhaps it would be moving the arm of a robot or something like that, right? So it's completely generic and agnostic in that respect.
Thank you.
Please just ask one question if possible. No follow-ups, please. The center microphone, please. Oh, you did it.
Thank you. I was excited to see your call for open source models. Are you also supportive of open source model weights and open source training data?
Okay, so certainly open source in the context of machine learning and AI is a complicated issue, right? Because you have the inference code. So right now, inference code for things like Llama 2 is open source. Okay, then you have the weights, the trained weights at various stages, right? Either just pre-train or fine-tune or whatever. And this is not source, right? It's a gigantic file of weight values. And so that should be freely available, but not like calling it open source has no meaning in that context, right? Then there is the training code, and most of the systems I talked about, the training code is not open for a number of reasons. And then there is the training data, and there's two types of training data. There is the pre-training data, basically just the text that is scraped from the internet or whatever. And then there is the data that is used for fine-tuning the system using human feedback. That second one is generally not public. It costs a lot of money to collect. Doesn't mean it shouldn't be public, but that's one of the reasons why I'm recommending open source platform, because if we crowdsource the fine-tuning, then this data will become public and basically become common resource. Then releasing the initial data, the issue with this today is that you can't even list which data you've been using because you expose yourself to lawsuits. And the reason being that the legal landscape of whether it's okay or not okay with copyright law to use scraped public data from the internet is not settled. Everybody is suing everybody in the US. I mean, like all the time in the US anyway. But in Europe they have some rule that you could opt out. In Japan they decided if it's publicly available on the web, it's kosher. You can use it to train your model. We're not going to sue you for it. So different countries have different approaches to this. And then communities of artists and writers are being really unhappy that their content is being used to train those models, and rich tech companies are making tons of money with their free labor or whatever. I mean, there's going to be lots of discussions over the next few years about this. It's not settled.
Thank you, Professor. So my question is about the use of AI in military. I know you mentioned that now we have abundant open source AI platform. So what do you think for the major governments in the world as well as smaller nations? Or what do you think about the future of humanity with the AI, the possibility that it could be used in military that create lethal weapons?
Right. So the systems that are currently used or being explored are not LLMs or anything like this, right? I mean, you can use LLM to some extent in some situations, but like most of I'm not at all in any kind of military involved in any kind of defense applications, but like most of the systems that are used are computer vision systems, basically, right? For detecting targets and things like that, automatically flying drones and this kind of stuff. And there's a question of morally, is it good or bad? Like, is it intrinsically good or intrinsically bad? Should it be banned? Is it okay? And what we see today is that the biggest use of those things is in Ukraine, for defense of Ukraine. So Ukraine has actually invested massively in drones. Most of them are teleoperated, but some of them now are kind of, have a little bit of autonomy in them and can recognize targets and stuff. I mean, it's all very secret, but it's pretty obvious that it's happening. And the war in Ukraine has really become a drone war, right? that are becoming increasingly smart. So this is a case where AI systems, lethal AI systems, are used for the defense of democracy, right? So is it intrinsically good or bad? I'm not a pacifist. I think this kind of technology should be used when it's, in the right hands, because it's going to be used by the wrong hands too.
I think currently we don't really have many real-world cases, but in the future, as AI getting more and more powerful and more open source stuff will be available.
No, that's not true. First of all, whether it's open source or not doesn't matter. Second, there have been autonomous weapons for a long time already. Cruise missiles, heat-seeking missiles, things like that, that are, once you shoot them, they're autonomous, basically. In fact, the oldest autonomous weapon is landmines. Landmines are autonomous, and they're banned by international treaties. And they're banned not because they are intelligent, but because they're stupid.
Professor. Question, first of all, I really appreciate the, there's been this long idea of how useful is the biological analog to sort of the artificial, so this concept of sort of the cognitive architecture as an agent model is an interesting one, sort of, and also your concept of the 4-year-old gets, 3 to the 15 bytes, that's a lot of training data. When we think about training efficiency, to your point, how many GPUs it takes to train these models right now, when we think about a 4-year-old learning the world model, is it sort of useful to think of that as 3 to the 15 bytes as full training, or is it some sense like humanity has done cognitive architecture search over 2 million years of evolution, and so that's actually more fine-tuning than it is an actual training run, and what does that mean for how much we should expect we have to do to get to something?
Right, so the answer to this resides in how much information is stored in the genome. Okay, so the genome is 3 billion base pairs. The base pair is 2 bytes. It's 2 bits, sorry. And so that's 800 megabytes for the entire genome. Right? The smallest LLMs that are practical at the moment are 14 gigabytes. So 800 megabytes is tiny. Now, within this, only a small portion is used for the brain. And within this, about 1% of the entire genome differs from humans and chimpanzees. So whatever humans do that chimpanzees don't do, like language or abstract, certain types of abstract thoughts, that has to fit in 1% of 800 megabytes. So it means 8 megabytes. That's tiny. You're not going to store like enormous amounts of prior knowledge, right? That in this, you're going to store like things like general connection architectures. Of the type that we do when we program a neural net, that we say, okay, it's a convolutional layer of that size, and then a transformer layer of this size, and how many heads, and blah, blah, blah. And, we read this code, and in the end, that corresponds to what the genome is storing. The other thing the genome is storing in us is the objective function. So in the system I described, there is intrinsic cost that kind of drive the system to learn certain things. And this is a good way for evolution to code into an organism a drive to do something without encoding how to do it. Like, evolution tells us that we need to feed when we're hungry. It doesn't tell us how. We have to figure it out. And that's a really good way of hardwiring a behavior without hardwiring the behavior, because that would be very expensive in terms of genome. So you can't rely too much on the genome. There's just not enough information there.
Thanks very much.
So unfortunately, we are out of time, and we could not take more questions. I see there are many more questions. But I would like to invite Professor Clavins back to the stage for concluding remarks. Thank you.
Okay, well, thank you all so much for coming. Thank you, Yann, for a wonderful talk.
Thank you.
It's great that you could spend time today with our community. We really appreciate that. I'd like to thank Mariam and Rico for organizing the lecture this year, and I'd like to thank the organizing crew for putting this together, and I'd like to thank the Lytle family and all of the donors that support that fund that supports this lectureship. There is a reception afterwards. You're all welcome to stick around. We'll be here for about another hour, so please do join us. And thank you once again for joining us, and thanks for a wonderful event.
Thank you.